Hi, in this video, we want to take a look at confidence intervals in statistics. All right, so the big idea here is that first, we come up with a point estimate of some value that we want to estimate in statistics. We're using our data. Now, after I get that individual value, that one number as my best estimate, I want some kind of gauge in how good of an estimate this is. So imagine the situation where we estimate the average height of, let's say, males in the United States. And in that average, we come up with the average height is 5'10". Okay. Now consider these two different situations. First situation, our estimate gives us a confidence interval of 5'9" to 5'11". Okay. So, that's a range of values. That confidence interval gives us an idea of realistic range of things that we could have. And there we would be like, wow, 5'10", that's a pretty narrow range. If 5'10" isn't quite right, I feel like I'm not very far off from it. Now imagine another situation. Let's say we get really wonky data, we see some really strange things, and we come to the conclusion that the average height of males in the United States is somewhere between 5 feet and 7 feet. Well, that's an awfully wide range. And honestly, that would show us that our point estimate doesn't really have a whole lot of reliability with it. We would have very low confidence in the individual value of 5'10", because it's such a wide range, it might be kind of far off. And the other one, when it's 5'9" to 5'11", we're pretty confident that our point estimate is close to the true value that we are trying to estimate. And so confidence intervals give us an interval of realistic values that the parameter that we're trying to estimate is equal to. And so we have a range of values, and if that range is really wide, we know we have less confidence in the individual point value. So in statistics, a confidence interval is a range of values constructed around a sample statistic that is used to estimate an unknown population parameter. Confidence intervals provide a measure of the uncertainty or variability associated with estimating the true value of a parameter based on a sample. Now, there's some key points that we need to talk about when we talk about confidence intervals. First one is that point estimates, which we talked about in a previous video. A point estimate is a single number that estimates the population parameter based on our data. For example, the sample mean is often used as a point estimate of the population mean. Next one is the margin of error. The margin of error is the amount of uncertainty or error associated with a point estimate. It reflects the variability in the sample and is influenced by sample size and the desired level of confidence. Next one is confidence level. The confidence level is the probability, actually, let's say the likelihood, that the confidence interval will contain the true population parameter. It is typically expressed as a percentage, such as 95% or 99%. The higher the confidence level, the wider the confidence interval. Construction of the confidence interval. Confidence intervals are constructed based on the principles of sampling distributions and probability theory. The most commonly used method is based on the assumption that the sample statistics follow a normal distribution or can be approximated by one. And we'll show examples of that in a little bit. Next one is the standard error. The standard error is a measure of the variability of the sample statistic, not of the sample, but of the statistic that we're interested in. It quantifies the average amount of deviation between the sample statistic and the population parameter. The standard error is used in the calculation of the margin of error. Calculations of confidence intervals. Confidence intervals are typically constructed around a point estimate using a formula that involves the sample statistic, the standard error, and critical values from the standard normal distribution, or t-distribution, or whichever distribution that we're using for that particular case. Most of the time, there's going to be a connection with normal distribution. And that's because of the central limit theorem. The critical values are chosen based on the desired confidence level and the sample size. Now, interpretation. This is the important step. Well, it's all important, but interpretation is critical. A confidence interval provides a range of plausible values for the population parameter. That's probably the most important sentence in this entire video right there. A confidence interval provides a range of plausible values for the population parameter. It is important to understand that the confidence interval refers to the process of repeated sampling rather than a specific interval that contains the parameter with a certain probability. Width of the confidence interval. The width of a confidence interval is influenced by several factors, including variability of the sample data, sample size, and desired confidence level. A larger sample size or higher confidence level will result in a wider confidence interval. That is a smaller sample. I have an error in this. A smaller sample size or higher confidence level will result in a wider confidence interval. Now, use and application. Confidence intervals are widely used in statistical inference to make conclusions about population parameters based on sample data. They are commonly used in hypothesis testing, estimating means, proportions, differences between means and proportions, regression analysis, and many other areas of statistical analyses. All right, so statisticians use confidence intervals on almost everything. Confidence intervals in hypothesis testing are specific to statisticians on how we approach data. Overall, confidence intervals provide a useful tool for estimating population parameters and assessing the uncertainty associated with those estimates. They help researchers and statisticians make informed decisions based on sample data while acknowledging the inherent variability and limitations of the estimation process. All right, so now something that is very common is to use confidence intervals while we're doing hypothesis testing. And so confidence intervals can be utilized in hypothesis testing, providing a complementary approach to traditional hypothesis testing, such as p-values. Instead of determining solely based off of statistical significance of a hypothesis, confidence intervals allow for estimating the range of plausible values of a population parameter. This estimation can aid in decision making and provide more comprehensive understanding of the underlying data. Here's how confidence intervals can be employed for hypothesis testing. Null hypothesis and alternative hypotheses. Beginning by formulating the null hypothesis and the alternative hypothesis, the null hypothesis typically represents the status quo or the absence of an effect, while the alternative hypothesis expresses the researcher's claim or the presence of a specific effect. Next, we choose the confidence level. So we select the desired confidence level for constructing the confidence interval. Typical choices are 90, 95, and 95%, 99%. 95% is by far the most common. A higher confidence level leads to a wider interval. Then we calculate the confidence interval. Using the appropriate formula and statistical methods, we compute the confidence interval for the population parameter of interest based on the sample data. The specific formula will depend on the parameter being estimated, such as the mean, proportion, difference between means, or difference between proportions. Next, we interpret the confidence interval. So we analyze the resulting confidence interval and interpret it in context of the research question. If the hypothesized value falls within the confidence interval, it suggests that the null hypothesis is plausible and cannot be rejected. Conversely, if the hypothesized value lies outside the confidence interval, it indicates evidence against the null hypothesis in favor of the alternative. All right, so the punchline of this section is this. If I'm doing hypothesis testing and I take a confidence interval, if the hypothesized value falls within the confidence interval, we fail to reject the null hypothesis. Conversely, if the hypothesized value is outside the confidence interval, we reject the null hypothesis in favor of the alternative. Next, we draw our conclusions. So we determine the conclusions based on the interpretation of the confidence interval. If the hypothesized value falls within the interval, one may reject the null hypothesis, implying that the data does not provide enough evidence to support the alternative hypothesis. If the hypothesized value is outside the interval, one may reject the null hypothesis, suggesting that the data provides evidence supporting the alternative hypothesis. Advantages of using confidence intervals for hypothesis testing. We get a range of plausible values. Confidence intervals provide a range of plausible values for the population parameter, offering more information than the simple point estimates. The next advantage is that we have assessment of practical significance. Confidence intervals allow for evaluating the practical significance of the estimated effect size by considering the magnitude and the direction of the interval. Next, the next advantage is that we have transparency and interpretability. Confidence intervals provide a straightforward interpretation that is often easier to communicate and understand than p-values. So here, I take that interval and I say, here's the range of plausible values that our data is giving us. And the next advantage of confidence intervals is that we have flexibility. Confidence intervals can be used for various population parameters, making them applicable to a wide range of research questions and hypotheses. It's important to note that confidence intervals and hypothesis testing are two distinct approaches, each with their own benefits and limitations. You should choose the one that works best for your audience. What will your audience accept is what you should choose to do. While confidence intervals focus on estimating the range of plausible values, hypothesis testing aims to evaluate the statistical significance of a hypothesis. Both approaches can complement each other and provide a more comprehensive understanding of the underlying data and research question. All right, so now let's talk about commonly used confidence intervals in statistics. The first one is going to be confidence intervals for a population mean. So I have some data and I want to estimate the true average coming from my sample population. This interval estimates the true population mean based on the sample mean. It is often used when the population standard deviation is known or when the sample size is large. If the population standard deviation is known or the sample size is large, you'll notice that here in this formula, I have a z for the normal distribution. So I have my point estimate of x bar plus or minus normal distribution value that corresponds to confidence level. I have the variance of my sample data, then I divide by 1 over the square root of my number of observations. This is here called the standard error. Now, if the standard deviation is unknown, or if the sample size is small, then instead of a z, I have a t. Now, here's something that is contradictory to a lot of statistics textbook. Professional statisticians almost never use this first formula. This first formula was primarily used back in the day when we had to use tables to do our computations. Now that we have computers that do everything for us, R, SAS, SPSS, whatever, what have you, there's really, for this type of problem, no reason to not use a t-distribution. All right, so here are some assumptions. So the bolded points are going to be the assumptions of each test. First one is that we have random sampling. The data that we have is obtained through a random sampling process. Next one is that we have normality. The population for which the sample is drawn follows a normal distribution, and we have independence identically distributed data when we are sampling. And so now let's go ahead and run run an example using R. So here I'm going to pretend that this is my sample. And if I run a t-test, it will go through and it will automatically give me that confidence interval. And one thing that's also really nice is that it'll actually run the hypothesis test for me very easily. It gives me the whole thing. Now you'll notice I don't use R to do a Z test. Why? Because statisticians professionally, for this type of problem, we feel like there's no need because the t distribution does a sufficient job. And base R doesn't even give you a Z test, even though it's in every single textbook on introductory statistics. And so now, after let's say I only want to get the confidence interval out of my test, what I can do when I run a test, I can say, hey, give me only the confidence interval, the $sign and the conf.int for the t.test will give me my confidence interval. And you'll notice it gives me my confidence level along with it. I can change the confidence level by going into my code and changing that. And that's true for all the tests we'll look at. Now, the next one we want to take a look at is confidence interval for population proportion. This interval estimates the true population proportion based on the sample proportion. It is commonly used when dealing with categorical data or binary outcomes. And so here we have our point estimate, sample proportions, and you'll notice that we have sample proportions times 1 minus the sample proportion divided by the number of observations inside square root. And then I'm multiplying by z. Here we're actually invoking the central limit theorem to be able to get this approximation using the normal distribution. Now, what are the assumptions of this? First one is that we have random sampling. The data is obtained through a random sampling process. Our data is independent, identically distributed observations. And we have large sample size. So the sample size has to be sufficiently large. That is so that we can invoke the central limit theorem. Typically, we require at least 10 successes and 10 failures to use this formula. And so now in R, if I want to run this after I have binary data, so zeros and ones for success failure, I just run prop.test. I indicate the number of successes, I indicate the number of observations, and it runs it for me. And so now you can see that prop.test does give me the confidence interval. It gives me the point estimate, just like the t-value. It runs the hypothesis test for me of inequality. Now, if I want to get only the confidence interval, when I run my test, I only extract the confidence interval and boom, I get it right here. And it'll give us the confidence level along with that for free. Isn't that nice? Now, the next one that we're going to take a look at is that we're going to look at the difference between two means. I want to evaluate what is the difference between two means. And you'll notice I've got a subtraction of the sample averages. I've got two populations, and I want to say, hey, do we have the same or different averages, or is one greater than the other? This interval estimates the difference between two population means based on the difference between two sample means is employed when comparing two groups or populations. So I've got two sample means, and I want to get a confidence interval based on the difference between them. So now here, once again, if both standard deviations, both variances are known and sample size is sufficiently large, I can use the normal distribution for this. If I don't know the standard deviation, or if the sample size is small, then I can use the t distribution on here, and it'll take care of it for us. Now, what are our assumptions? First of all, we have random sampling, so we want independent, identically distributed random sample. Both data populations are obtained through random sampling. We have normality. The populations from which the samples are drawn follow a normal distribution. We have independent, identically distributed observations for population 1 and population 2. The observations within each sample and between two samples are independent. And now here, homogeneity of variances. This is not required. There's actually a different formula for this, but I didn't show it because really we'll just let R take care of the difference. But here we can possibly have the assumption that our two variances, two standard deviations, are equal to each other. And when I run my t-dot test, if I believe I have the same variance for both of them, I'm going to say that I want pooled variance on this. Here, I'm running it assuming that we don't. If you don't know, if you're unsure, say that you don't have pooled variances. That will make us more prone to failing to reject the null hypothesis also. And so here, once again, we're going to get our confidence interval. And here we would reject the null hypothesis, favoring the alternative that the true difference between the means is not equal to 0. So you notice that 0 is not in this interval. So I would conclude that there is a difference between the average of these two populations. Here are the point estimates of each mean. And if once again, I can do conf.int to extract the confidence interval, that also gives me my confidence level. Now, similarly, we can do a confidence interval for the difference between two population proportions. So I want to see if two different populations have the probability of success equal to each other, or maybe I want to get the range of the values for the difference between the proportions. So this interval estimates the difference between two population proportions based on the difference between two sample proportions. It is used for comparing two groups or populations with categorical data. So here I'm looking at the difference between proportions. And here I have this standard error formula. And one of our assumptions is that we have random sampling, that the data for both samples are obtained through a random sampling process. We have independence within each sample and between two samples are independent of each other. And we need a sufficiently large sample size. So for us to be able to invoke the central limit theorem, which gives us that Z, the sample sizes for both groups have to be sufficiently large. So we want at least 10 successes and 10 failures in both groups. And so now to do this in R, to get the difference, once again, I use prop.test, but this time I have to set up a table of numbers indicating the number of successes and the number of observations for each of these. And so you'll notice that here I have a proportion of 0.6, proportion of 0.7. My two point estimates are 0.54, 0.74. Here's that p-value. And here is that confidence interval. So here you'll notice that 0 is not in my confidence interval. So my hypothesis test would say 0 is not in the confidence interval. Therefore, the difference, the data indicates that the difference between the two true proportions is not equal to 0. That means that they're different from each other. Now, if I look back up here at my code, I know that one's 0.6 and the other one is 0.7. So I know that there's a difference. So the way I generated this fake dummy data confirms that we're getting the correct conclusion. And to get my confidence interval, all I do is once again use conf.int on there to extract it, and boom, I've got it. Now, the next one to talk about is confidence intervals for regression coefficients. So this will be for the slope or the intercept in a simple linear regression model, or any of the coefficients in a multiple linear regression model. So in regression analysis, this interval estimates the true value of the regression coefficient based on the sample data. It helps assess the significance and the direction of the relationship between the variables. And so here, this formula, I put down the generic formula because we'll have the intercept, or we'll have the slope, or the coefficient, depending on what the model is. And the standard error is a little bit different depending on if it's intercept or slope. And so I just put down the generic one. So the first assumption we need to have to run a confidence interval for regression is that we need to have a linear relationship between the dependent variable and the independent variable. Otherwise, regression doesn't even make sense. Next assumption is that we have to have independence between our observations. Next is homoscedasticity. The variance of the errors is constant across all levels of the independent variables. And then we need normality of the errors. The errors, or residuals, follow a normal distribution with constant variance, and the residuals are independent of each other. So to run this, I can go through. I have a linear regression model. LM is linear model. And then to get it, I just go ahead and to get the confidence interval of the slope, I can do conf_int for the model. It will give me multiple. If I only want the slope, I just indicate the predictor variable, and here we get it. So now I have my confidence interval. Now the true value is 3. I know it's 3 because I generated this fake data. And so we can see, yeah, 3 is in there, and the values are, relatively close. They're not super, super close. If I had more data, this would be tighter. Now, the next one we want to talk about are hazard ratios from survival analysis. This interval estimates the true hazard ratio based on the sample hazard ratio. We use this to analyze time to event data. And so here the formula for us is the log of the hazard ratio plus or minus z times the standard error of the log of our point estimates. Now we have assumptions on this. So we have, our first assumption is that we have proportional hazard assumption. The hazard or failure rates of the two groups being compared are proportional over time. And we have independence between our observations. And so if I want to get a confidence interval for this situation, I'm going to need to use the survival package. So here is my time just being generated. Survival analysis typically uses exponential distribution for that. And here is the status, and I'm just generating fake dummy data here. Here's the group being generated as fake data, putting it into a data frame. And now I'm going to go through and do my Cox survival analysis model. So I want survival analysis where time and status depends on the group. I indicate which data I put in here, and then I put it into the function. And so now to get my confidence interval, remember that we had the whole logarithm thing going on. To get the confidence interval, I can do the confidence interval off the model. I specify which one I want. And then to undo the log, I take an exponential. And this gives me a confidence interval of the group 2 aspect. Now the next one we want to take a look at is the confidence interval for the variance. So this interval estimates the true population variance based off of the sample variance. This should feel familiar to the previous ones we looked at. This is commonly used in quality control and process improvement studies. And so here, this one looks a little bit different. This one is a little bit more interesting, that we have that our population variance is between n-1 times sample variance divided by this. Here, it's a chi-squared. And then on the right-hand interval, it's n-1 sample variance squared. And now you'll notice that the chi-squared almost looks the same, but here I have alpha over 2. I have 1 minus alpha over 2. And so, there's something going on here. So our assumptions, we need random sampling. The data is obtained through a random sampling process. We have independence between our observations, and we have normality. Remember, whenever we're handling the chi-square distribution, more than likely, we're assuming that we're we're looking at the variance from a normally distributed sample. The population from which the sample is drawn follows a normal distribution. And so now to get this confidence interval, I'm going to need to invoke a special package. Here I'm just generating my data, my fake data, and we use var confidence interval, variance confidence interval on a sample. Boom, we get it. And so here is the point estimate, and then we get the upper bound and the lower bound of our confidence interval. Now, the next one, we can get a confidence interval for the median. So here we're going to estimate the true population median based on sample data. And so this is, we often choose to do this when our data is skewed, does not follow a normal distribution, and we feel like the mean is not appropriate. We want to use the median instead. So our assumptions, once again, is that we have random sampling, that the data is obtained through a random sampling process. Our data is independent and identically distributed. And here, there's a little bit of a difference how we compute this one way or another. If you take a non-parametric statistics, we'll dig into this aspect. But here, I'm just going to just throw this out here. We prefer if the population comes from a symmetrically distributed population. But typically, if we had that, we would more likely be using the mean. So this one is definitely optional, not necessary. And so once again, if I'm going to get a confidence interval for the median, I'm going to use the same package I used a moment ago for the variance. And this time I just do median confidence interval. Boom, it gives me what I want. Here's my point estimate. Here's my lower bound and my upper bound of my confidence interval. So these are just a few examples of commonly used confidence intervals. The specific type of interval depends on the nature of the data and the research question being addressed. All right, well, that's all I've got for you. Life is short, do math.